Let us see the chemical reactions of haloalkane. They are of three types. The first one is nucleophilic substitution reaction. Now nucleophiles, they are nucleus loving or electron donating, and they can be neutral molecule or negatively charged ions. Now in this reaction what happens is weaker nucleophile are replaced or substituted by stronger nucleophiles. Here a general reaction, X can be any halogen plus, now here halogen, they themselves are nucleophile. Now this nucleophile will be replaced by a stronger nucleophile which is sodium, and as a result the product will be RNA. It is replacing the weaker nucleophile with a stronger nucleophile. Same follows in the second case. One nucleophile is replaced by the other nucleophile. Here we have the negative nucleophile. So this nucleophile get replaced by this nucleophile in this case. And we are left over with the first nucleophile. Even if we don't try this, it's fine. We just have to show how the exchange or replacing take place. Nucleophilic substitution reaction takes place through two different mechanisms. The first one is SN1, also known as substitution nucleophilic unimolecular mechanism, and SN2, that is substitution nucleophilic bimolecular mechanism. Now let us see the first one, which is SN1. In this reaction, it takes place basically in two steps. In the first step, the halogen atom, let me show you with the example. This halogen atom will be lost and a carbocation having a positive charge, that is the carbocation, will be formed along with a halide ion. This is the carbocation and this is the halide ion. So in the first step, from the haloalkane, the halogen will be lost, resulting in the formation of a carbocation and a halide ion. In the second step, once the carbocation is formed, it will be attacked by a nucleophile and the product will be formed. Now we have the carbocation. It will be attacked by any nucleophile. Let us take Na plus as a nucleophile in this case. Now it will attack the carbocation, the carbon, and it will give us this product. Now more the stability of carbocation, faster will be the rate of the reaction. If we have primary haloalkane, that means 1 degree haloalkane, this one. Why is this 1 degree? Because the carbon which is attached to a halogen is attached to only one alkyl group. If it is attached to 2 alkyl group, it will be 2 degree. If it is attached to 3 alkyl group, it will be 3 degree. Now this, the halogen will leave and it will give you a carbocation. In case of 2 degree, you will get carbocation in this manner. And in case of 3 degree, where the carbon is attached to 3 alkyl group, the carbocation will be. Now in this 3, first, second and third degree haloalkane, more the number of alkyl group, more stable it will be. That means the reactivity order will be in this manner. 3 degree will be more reactive, followed by 2 degree, then the least will be for 1 degree. 1 degree is the least stable, highly stable, and the moderate one. So in this SN1 reaction, the formation of this carbocation takes place, and this carbocation which is formed, as per the rule, nucleophile will come and attack it. Now the attack can be from the front as well as from the back. We have our carbocation. The nucleophile can attack from the front as well as from the back. Now if it attacks, we have our nucleophile here. If it attacks from the back, we will get Na in this manner. The bond needs to be maintained, 1 to 3, 1 to 3 bonds. And if it attacks from the front, here we get this as a product. If the halogen was polarly active, that means which can rotate the plane polarized light. Plane polarized light means those which are unidirectional. Now those compounds which rotate the plane polarized light towards right. If it rotates towards right, it is known as dextrorotatory or deform. If it rotates towards left, it is known as levorotatory or L-form. How will you know whether it is rotating in right or left? Now if the nucleophile after attack it is placed the left hand side, it is the L-form. If it is placed at the right hand side, it is the D-form. Now our next criteria is that if our reactant having the halogen, if the halogen is placed at the right hand side, it is the D-form. Now after attack of the nucleophile, if the product form is also D-form, that means the attack happened from the front, then it is said as retention of configuration. Retention of configuration has taken place here. Retention. Now the second case is that if the attack happened from the back, our reactant is in the D form, that means right. But if the attack happened from back, we will get the product as in this manner. So this is the L form. Now reactant is in D form, product is in L form. So here it is known as inversion of configuration. What is this configuration? D form, L form, these are known as configuration. Now if both the forms are possible, D and L form, we will get equal mixture of D as well as L form. Now this equimolar mixture of getting D and L form will give rise to racemic mixture. That means if retention and inversion has taken place, it will be a racemic mixture. Now let us see what is this SN2 mechanism. In this SN2, the nucleophile will attack the carbon carrying the halogen before the halogen has left the carbon. Now this will lead to the formation of a transition state which is quite unstable, and therefore it dissociate or break down to give the final product. Now in our SN1, what was happening was that The halogen leaves first, carbocation is formed, and the nucleophile attacks the carbocation. But in your SN2, the nucleophile will directly attack the main product even before the halogen has left. So in this case, what we will get, halogen, now this nucleophile cannot attack here. Front attack is possible only when the halogen has left and it requires a positive charge. So now there is only one possibility of your attack, that is the nucleophile will attack only from the back position. From the front position it's not possible because halogen is present. Now upon this we will get NaC. Now this bond 1, 2, 3, 1, 2, 3. Okay, we have to maintain the tetravalency. Now Na will come and attack here. Now here, okay, firstly let us not see about the tetravalency. Let us keep as it is. Na will go and attack. Will attack here from a bond, and this 3 bond will place itself. It can place here, it can place here. It's fine wherever it can place. Now here we get this. We get a transition state where the halogen as well as the nucleophile is attached to the carbon atom. Nucleophile as well as halogen is attached to the carbon atom. Now as we proceed further with this reaction, the bond between halogen and the carbon weakens. It weakens, and if this weakens, this bond starts becoming stronger. Now as a result, since it weakens, it will start breaking. This bond breakage will take place and we will get Na in this manner. Now the tetravalency is maintained. Initially, we were not maintaining the tetravalency because the bond breakage was going to take place. Now, in this, only inversion is possible. Retention is not possible. You can see here why retention is not possible, because Na cannot attack here because halogen is present. It can attack only from the back. That is why inversion is possible, no retention is possible. Even in this case, more the number of alkyl group, the attack of nucleophile will be hindered. So lesser the number of alkyl group, the more easily nucleophile will attack. In SN1, we saw that 3 degree is more stable, followed by this. Now in this case, SN2. In 3 degree, 3 alkyl group is present. In 2 degree, 2 alkyl group, and in 1 degree, 1 alkyl group. Now in case of SN2, more the number of alkyl group, more alkyl group, the attack of nucleophile will be hindered. Simply you can say that more alkyl group, nucleophile will not be able to attack. So in this case, which will be stable? 1 degree more stable, followed by 2 degree, and the least one will be 3 degree because it has the highest number of alkyl present, and this has the least alkyl present. Now let us see the third type, elimination reaction. In this reaction, when haloalkane reacts with alcoholic potassium hydroxide solution KOH, beta hydrogen and halogen will be lost from that particular molecule, and as a result we'll be getting alkene. Now what is beta hydrogen? Here the carbon which is directly attached to halogen, it is your alpha carbon, and the second one is your beta carbon. So this is your alpha hydrogen, this is your beta hydrogen, and the next one becomes the gamma. Now here let us see one example. We have chloroethane, just for example. Now here, when this haloalkane will react with alcoholic KOH, this is our alpha, this is our beta. So in this case, what will happen is the halogen as well as one hydrogen from this beta carbon will be lost. This will be lost and one hydrogen will be lost. As a result, we will get CH2 double bond CH2. So this is our alkene, ethene. Now this reaction is also known as hydrohalogenation reaction. Why? Because here hydrogen and halogen are lost, and since hydrogen is lost from the beta position, this is also known as beta elimination reaction. Now if we have a reactant and we get two different types of product, so in that case more highly substituted alkene will be preferred as the major product. Now let us see one example. If we have such type of reactant where the carbon attached to the halogen is the alpha carbon and the carbon next to the carbon which is attached to the halogen will be the beta carbon. So in this case we will have two beta carbon, that is, this is one beta carbon and this is the other, because both of them are present just next to this carbon which is attached to the halogen. So in this case, whenever we have two beta carbon, we will be getting two types of product. According to the elimination mechanism, halogen will leave as well as one hydrogen from the beta carbon, or the beta hydrogen will leave. Now either the hydrogen can leave from here or here. If in the first case the hydrogen leaves from here and the halogen also leaves, we will get CH3, CH2, CH2, CH double bond CH2, because one has left from here, so it becomes a double bond. This is our first case. And the second case will be, or if it leaves from here. If it leaves from here, the double bond will be coming here. CH3, CH2, CH2 double bond CH2, CH3. Now from these two, which will be our major product? According to Sedzev rule, it says that whichever product has the highest substitution, that will be our major product. So in this case we have one methyl group, but in this case we have two methyl group. So this has the highest substitution, so this will be our major product and minor product. Now what is major and minor? Major means we will be getting this in a large amount and this one in minimal amount. Now let us see how haloalkane reacts with metal. Haloalkane mostly react with different type of metals and they give different products, which will depend upon the nature of the metal with which it is reacting. Now if haloalkane react with active metals like aluminium, lithium, zinc, it gives rise to organometallic compound. Organometallic compound are those in which the metal is directly linked to the carbon atom. Now there is one more special case where if halogen react with magnesium metal, they will give rise to a special type of organometallic compound known as your Grignard reagent. This reagent is very important. Haloalkane also react with sodium metal to give alkane. Now let us see some of the reaction. We have the haloalkane C2H5Cl. When it reacts with active metals like lithium, in presence of dry ether, it will give rise to an organometallic compound such as C2H5Li. This is ethyl lithium. In this case, the lithium will be directly bonded to the carbon. Now, if 2 moles of haloalkane react with another active metal, zinc, in presence of dry ether, it will give 2 moles C2H5 twice zinc. This is diethyl zinc. Now let us see the second case where haloalkane reacts with magnesium to give special type of organometallic compound. We have haloalkane which react with magnesium to give special type of compound which is known as your Grignard reagent, C2H5MgCl. This is known as ethyl magnesium chloride or alkyl magnesium halide, or famously known as Grignard reagent. In the first case, organometallic compound, simple organometallic compound, we have observed that the metal is directly linked to the carbon. In this second case, a halogen atom as well as an alkyl group is linked to the metal atom. No matter we have written in this manner Mg and Cl far away from carbon, but the real structure consists of this alkyl and halogen attached to the carbon. Even in case of organometallic, the first case, the metal will be directly linked to the carbon. Now let us see the third case where halogen reacts with sodium. Haloalkane reacts with sodium in presence of dry ether to form alkane as the main product. Now, this reaction where alkane is formed is known as your Wurtz reaction. Now suppose we have 2 moles of haloalkane, 2 moles of sodium, dry ether, we get alkane, and 2 moles of NaCl as the byproduct.